present about the result of our research regarding with the nonlinear finite element analysis of full-scale external post-tension concrete box curve and checking and surface condition. As we know that the concrete cracking is potentially occur in the deviator and also in the anchorage of the box curve, especially for the external portion. And actually, it is not totally avoidable. Why? Because not all section of the box curve is compressed in three direction, especially for the deviator and anchorage segment. The several investigations have shown that case of the cracks in the deviator and diaphragma segment when using the external test. So in this research, we would like to conduct the more detailed investigation about the response of the segment deviator and end segment regarding with the cracking behavior, and then second if about the global structural response regarding with the load and deflection capacity of the curve. This is the geometry of the box curve. The total span of the box is 47 meters, with the distance from the support is 45.2 meters. This is the cross section of the box curve in the anchored segment in here. It's like this one, and then in the middle there is two deviator in here and in here, with the cross section is like this one. The width of the bridge is 14.3 meters, and the height of the box curve is 2.6 meter. And it is same, yeah. There is ordinary segment over in here, S1, SV, and so on. Actually, this box curve have designed put in the cross section and also the reinforced according to the standard to resist the life load. But we would like to know about the response of the concrete in this area, about the possibility of the cracking in here. It is the more detailed reinforcement in the end segment in this area, and then in the deviator segment in this area. In this research, we use our in-house software, LD and LV, and then it is the visualization of the model. It is the concrete. It is in the inside there is tendons, and it is the anchorage segment. In here there is deviator, yeah, deviator in here, and over there is the end segment. To make this model, a group of element and boundary condition model were created using Salem 9.3.0 software. And then for running this model, we use 3D and LV, three-dimensional nonlinear finite element analysis. And then the result of this modeling, we use the Parafill 5.9.0. Actually, in the process of the modeling, we have to match the model. It is the visualization of the matched model. The solid tetrahedral element with 4 nodes are used to model the concrete structures, and then the pre-stressed tendons and also the steel anchors. The modeling of steel anchors is simplified to a thin solid cylinder input side, and then there is support in here. Like this one, this LRP lead rubber bearing is modeled using solid element as in this support. In this box here, there is reinforcement. It's modeled using embedded truss element, and then the contact between the concrete and the reinforcement or the tendons is modeled as perfect bond. Actually, we are focused in the end segment and deviator, so we make a more detailed analysis in here by using the mesh size 100 millimeter. It is the more detailed constitutive model for materials for this concrete. The compressive strength of the concrete is 14 MPa, and then there are some constitutive model both for compression and also for tension properties of the concrete. The concrete constitutive model is use the multi-surface plasticity model, which compares the compressive failure surface and the tension cut of the failure surface. More details in this refers. And then the constitutive model for the concrete under compression has a non-associated flow rule, and then the concrete under tension follow the associated flow rules. Actually, the stress strain for the concrete using the Attard and Stange model, and then the hardening function using the Calazzo et al. 2013. For the softening during the tension, the stress strain using the Hofer and Passan formula. And then the focus in the series is regarding with the crack width in the segment deviator and the end segment. So we are focused in the crack width. That function to indicate the pattern of the crack that occur and the size of the crack opening and then. Okay. The next is the constitutive model for the steel and also the pre-stressing steel. For the first is for the mild steel, we have the ordinary steel, 420 for diameter larger than 13 millimeter, and also we use the 15.24 millimeter for pre-stressing steel or strength with the following characteristics. And then for the properties in elastic stress-strain relationship, we use the multi-linear models for the plasticity. Loading sequence, in the first step, we apply the checking force in this modeling. The self-weight of the bridge, it is calculated in the model, and then in the second step, we apply the point force in here with the supporting input side as 3 point bending to replicate the typical wheel axle from vehicles, or we look as live loads. And in the results, we are focused on the two. The first is the flexural performance, and the second is about the nonlinear response in the deviator and in the end segment. It is the flexural performance of the box girder regarding with load displacement relationship in the mid-span at checking condition. Actually, if we apply the force in the tendon, the girder will deflect in upward direction. Actually, from this model, the behavior of the bridge is almost linear, until 100% of checking force is transferred to the girder, and it is the deflection or chamber of the box in the middle span is 38.9 millimeter. And then the next, it is the behavior of the load and displacement relationship at the span at surface due to the point load. The downward deflection occurred in line with the increased load. The curve stand for the final to do the pre-stressing is for the last in checking condition, 38.9 millimeter. We applied the concentrated force in the middle span of the bridge, so it is the results. Actually, the curve is linear until load 7,000 kilonewton. 7,000 kilonewton. But in the design, we just required around 4,000 kilonewton. So our bridge have adequate capacity to resist the life load.
You have 1 minute more.
Okay.
And 2 minutes.
Yeah, thank you. But in this result, we obtained nonlinear cracking in the segment, end segment, and also deviator like this one. But in the ordinary segment, there is no any cracking. According to our observation, the maximum crack width in this area is just 0.08 millimeter, and it is not still in allowable maximum limit, so it is no problem. And for the repairing, maybe we just using the surface sealing. And actually, regarding with the stress strain in the reinforcing steel, in this figure shown that the steel parts, it is under the yield stress. So it no problem. And then the last is conclusion. Actually, we have conducted the pre-stressing modeling for this box kiddo using 3D and LV package, the provided section and also reinforcement, and also pre-stressing force produce box kiddo with adequate flexural strength to receive the self-fit and also the life load. Under surface limit condition, the load displacement curve remains linear at elastic condition. And actually, high concentrated force due to checking transfers at the end anchorage and also the viator segment cause cracks in the diaphragm with why? Because the stress is exceeded the permissible, but the crack width it is in allowable crack. And after that, the stress in the concrete is resisted by the steel. Thank you.
Great. So we can take one or two questions. Yes, right.
If somebody else wants to ask.
Yeah, go ahead.
I have actually another question. I have remarked. I noticed the compressive strength that you used was 40 MPa, which is very, very less as recommended PSI. It should be between 50 to 60 MPa for prestress concrete. Number one. Number two, the strands, the yield strength I noticed was about 1500 Pascal, right? It should be 270,000 PSI is about 1862 MPa. Can you explain this difference?
Okay. Actually, why we use the just 40 MPa because the reinforcement detail in this segment is so cohesive. So if we need more flow concrete, so it is and actually with the strength it is adequate for the structure. For the first question, can you repeat for the second question?
The second question was the yield strength of the strand that you showed was about 1500 MPa. It should be more than 1800 MPa as per PCI.
Oh, yeah. This one?
Yeah, yield strength is
Yeah.
okay.
Okay.
Tensile strength FPU. I'm talking about the yield strength. Yield strength should be more than 1800 MPa.
Okay. But actually, in this model, we use usually used in Indonesia. We use these properties for the steel reinforcement and also for the pre-stressing stuff like this one. Maybe it is possible we use the higher compressive strength and or higher strength of the steel. It's no problem. Maybe it is the good suggestion for us to make the future.
Great.
But once you jack at such a high pulling force, the 40 MPa will crack.
Okay. For the pre-stressing force, it is 0.75 from FPU. It is the maximum.
That's okay, 70% or
Okay.
75% of the yield strength.
Yeah. Well, so I think we go to the next presenter online.